Hey everyone, and welcome. Every single day we use these amazing devices that, honestly, they feel like pure magic. But today, we're going to peek behind the curtain. We're going to uncover the secret blueprint that powers our entire digital world. Yeah, we're talking about computer architecture. Let's dive in. Just think about it for a second. You tap an app on your phone, you fire off an email, you just move your mouse across the screen, and it all just works. It feels completely seamless, instantaneous. But underneath that smooth experience, there's this incredibly complex dance of logic and electricity going on. So what is really happening in there? Okay, so to understand what's happening, we've got to peel back the layers. And the first thing you have to get is that computers don't speak our language. They don't even really speak programming languages, not directly. There's this whole translation process that has to happen first. So it all starts here, with something called a high-level language, like C++. You can see why they call it high level, right? It's kind of readable for a human. A programmer can look at this and understand the instructions. But for the computer, this is just gibberish at this point. It's only the first step. Then, that human-friendly code gets fed into a program called a compiler, which chews on it and spits out this. This is assembly code. As you can see, it's way more cryptic, much more machine-like. We're getting closer to the hardware, but believe it or not, we're still not at the language the computer actually understands. And here we are, binary, just a pure stream of ones and zeros. This, right here, is the only language the processor, the brain of the computer, actually speaks. This whole process, going from a language we can kind of read down to the machine's native tongue, is a super important concept called abstraction. It's the magic trip that lets us build these incredible systems without having to think in ones and zeros all day. So, who designs this whole complicated system? Well, it really helps to think of it as two different roles, two different minds. You've got the architect who dreams up the blueprint, and then you've got the engineer who figures out how to actually build the thing. The best way to get this is with a car analogy. Think about it. When you're the driver, all you need to know is what the controls do. Turn the wheel, the car turns, press the gas, the car goes. That's the architecture. You don't need to know how it works under the hood, right? Whether it's power steering or what kind of engine it is. All those details are the organization. So let's make that official. Computer architecture is that high-level driver's view. It's the functional blueprint. It defines the what to do. It's everything a programmer needs to know to make the computer work without worrying about the guts inside. And computer organization, well, that's the under-the-hood stuff. It's the physical implementation of that blueprint. It's all about the how to do it. How are the circuits actually connected? How do the signals flow? It's all the deep-down engineering that makes the architect's vision a reality. All right, now that we have those two big ideas down, let's go see them in action. Let's take a tour of the most critical component of any computer, the CPU, the central processing unit, or, as you can think of it, the brain. At its very core, the CPU is constantly doing this simple three-step dance, and it's doing it over and over, billions of times every single second. It's wild. First, it fetches an instruction from memory. Then it decodes that instruction to figure out, okay, what do they want me to do? And finally, it executes the command. Fetch, decode, execute. That is the constant heartbeat of your computer. Now, inside this brain, there are a few key players. You've got the ALU, the arithmetic/logic unit. Think of it as the super fast calculator doing all the math. Then you have registers. These are like tiny lightning-fast little sticky notes for data the CPU needs right this second. And finally, you have the control unit. It's the traffic cop, directing the flow of information everywhere, making sure that whole fetch, decode, execute cycle runs without a hitch. Okay, but this brings up a really good question. If all CPUs are basically just doing the same dance, why are there so many different kinds of them? Why is the chip in your laptop completely different from the tiny one in your smartwatch? Well, it all comes down to balancing priorities. And this is the perfect example of the core trade-off. A laptop CPU is built for one thing, raw performance. It's incredibly fast, but it absolutely chugs power and gets hot. A smartwatch chip, on the other hand, is playing a totally different game. It's all about efficiency. The performance is way lower, sure, but it can sip power and run all day on a tiny battery. So you see, these are the fundamental choices every chip designer has to make. Are we going for maximum speed no matter what? Or is long battery life the most important thing? How much can this thing cost? And is it a general-purpose chip for a desktop, or is it a super specialized one that will only ever do one thing? The answers to these questions shape the final design. Okay, so let's bring it all home. Let's put these two big ideas, the blueprint and the build, side by side for one final, crystal clear comparison so it really sticks with you. So really, it all boils down to this. Architecture is the what. It's the high-level, functional blueprint that a programmer sees and uses. Organization is the how. It's the low-level, nitty-gritty physical parts, the circuits and signals that actually make it all work. One is the blueprint, the other is the actual physical building. Now, before we finish up, I want to leave you with one last kind of mind-blowing thought. This whole world of processors and blueprints, it isn't just for your laptop or your phone. They are the invisible brains, the ghosts in the machine, inside pretty much everything we use every day. We call these embedded computers. They're not designed for browsing the web or playing games. They are intelligent parts designed for one single, highly customized task, like making sure the engine in your car runs perfectly or controlling the spin cycle on your washing machine, often happening in real time. And that really leaves us with a final, massive question. Every single year, billions of these tiny, specialized brains are being created and woven into the fabric of the world around us, making everything smarter and more connected. So as this trend just keeps accelerating, what does this invisible layer of intelligence, all built on these principles of architecture and organization, what does it truly mean for our future?